Welcome back to the ANSYS 2D Meshing Masterclass. In today's session, we'll understand one of the most important concepts in FEA meshing, the different element types, quad, tri, and quad dominant. This single decision often defines both the accuracy and the overall performance of your simulation. As always, the link to the previous tutorial is available in the description box. Make sure you watch it for better understanding. And if you need project or thesis support, my contact details are also provided in the description. In this lesson, we are going to break down each type of 2D element used in ANSYS meshing, understand their strengths and limitations, and see exactly where each one performs best. You will learn how triangulated meshes behave, why quadrilateral meshes are often preferred for structural analysis, and how quad-dominant meshes give a practical balance for complex geometries. By the end, you'll be able to confidently choose the right element type for any 2D meshing problem. Before we actually mesh anything in ANSYS, it's important to know what each element type means and when to use it. The element type controls how curvature and boundaries are captured, how stable and accurate the solver becomes, and finally, how long your simulation takes to run. That's why choosing the right element is not just a meshing choice, it's an engineering decision. Let's start with triangles. Triangular elements are the most flexible and the easiest for meshing tools to generate. They can fit everywhere, even in areas where the geometry is highly irregular. In ANSYS, we can generate a triangular mesh directly using face meshing by selecting triangle as the element type. Triangular elements are extremely flexible. They fit almost anywhere: irregular shapes, sharp corners, twisted geometries, or tiny patches. They fill the entire domain even when the geometry is very complex. That's why automatic mesh generation in many tools defaults to triangles. But the trade-off is accuracy. Triangular elements generally behave stiffer, especially in bending. This can cause over-prediction of stress because the mesh resists deformation more than it should. So remember, triangles are easy to generate and great for complex shapes, but usually less accurate compared to quads. Now let's move to quadrilateral elements. Quadrilateral elements are the engineering favorite because they provide better accuracy, smoother stress distribution, and improved bending behavior. In ANSYS, quad meshes can be generated using face meshing or by guiding the mesh through proper partitioning. Quadrilateral elements capture bending much more smoothly, provide better stress gradients, and reduce the total number of elements required for the same accuracy. If your goal is high-quality structural results, use quads wherever the geometry allows it. Quads are best for beams, plates, and shell-like parts, components with long, straight edges, regions with stress gradients, thin or slender parts. Quads give cleaner stress contours and converge faster, but they depend heavily on the geometry being clean and well partitioned. If the shape is irregular, the mesher may struggle to create a pure quad mesh. So in complex geometries, you often need to split the model into smaller logical regions before applying quad meshing. Now let's look at how triangular and quadrilateral elements behave in real 2D meshing inside ANSYS. I'll start with a simple square geometry. First, I apply face meshing with triangle's best split mode. Now click on Generate Mesh. After generating the mesh, we use Display State Element Quality to check the mesh quality. We get a minimum quality of around 0.86. This is acceptable, but you can clearly see random diagonal splits and slight irregularity across the region. Now I switch the same geometry to face meshing with quadrilaterals and regenerate the mesh. The quality now jumps to 0.999, which is essentially perfect. Why do quads perform so well here? because a square is a naturally structured shape. Quadrilateral elements align cleanly with straight boundaries, they maintain orthogonality, and ANSYS doesn't need to distort them to fill the region. So for regular shapes like rectangles and straight-edged domains, quad mesh consistently produces the highest quality with fewer elements. Now let's move to a more challenging shape, a U-bend geometry. First, I apply quadrilateral face meshing. When we generate the mesh, the quads near the inner bend become severely stretched and skewed. The minimum element quality drops to 0.198, which is too low for structural accuracy and would cause stiffness inaccuracies. Next, I switch the method to triangle's best split mode and regenerate. Instantly, the mesh adapts better to the curvature and the minimum quality increases to about 0.556. Why does the tri-mesh perform better here? Because triangles are naturally flexible. They can rotate, shrink, and fit smoothly into tight curves without forcing the mesh into unnatural alignment. In regions with bends, organic shapes, or irregular boundaries, triangles provide higher minimum quality and smoother transitions. Now let's talk about quad-dominant mesh, the perfect balance between flexibility and accuracy. ANSYS generates mostly quads, but fills small leftover regions with triangles. This gives you the benefit of quad accuracy without the headache of forcing a pure quad mesh in tricky areas. Think of quad-dominant mesh as 90% quad performance, 10% tri-flexibility. This is one of the most practical options for real engineering geometries. And don't worry, we will discuss quad-dominant mesh in much more detail later in the series. Before we close, here's the rule of thumb used by many FEA engineers. If accuracy matters, prefer quadrilateral elements. If the geometry is complex, use triangular or quad-dominant. If time is limited, triangular mesh is the fastest. And in most engineering projects, quad-dominant mesh gives the best balance between performance and accuracy. Before we close, a quick note. We also provide project and research assistance for students, professionals, and industries. Whether you need help with CFD, FEA, thermal analysis, optimization, dynamic mesh, multiphysics, or advanced simulations in ANSYS, Abacus, Star CCM+, SolidWorks, OpenFOAM, and more, we support academic projects, final year work, MTech PhD research, industrial case studies, and simulation-based consulting. If you need guidance, collaboration, or simulation support, feel free to contact us. Your project success is our priority. And if you found this tutorial helpful, make sure you like, subscribe, and turn on notifications to stay updated with our upcoming tutorials and CFD and FEA videos. Thank you for watching. See you in the next video.